Rudewright Academy. Learn it, teach it, remember it. Today we'll learn Dijkstra's algorithm. It finds the shortest distance from one starting point to everywhere else, across a whole network of connected roads. Let me show you how it works. Picture a map of cities joined by roads. Each road is marked with its length. We want the shortest route from A to F. On a real network, the routes number in the thousands. And yet, the answer appears almost at once. Here is how it works. Imagine pouring water in at the start. It spreads down every road at a single constant speed. The instant it reaches a city, you have arrived by the shortest route, because the water tried every path at once. The nearest cities are touched first, then the next nearest, like ripples spreading from a stone. Here is our concrete example. 6 cities, 8 roads, each with a length. We start at A. We want the shortest distance to every city. To F, most of all. One condition makes this work. Every road must be 0 or longer, never negative. First, one term you'll meet everywhere. We relax an edge. Every city keeps a guess at its distance. Infinity to begin with. Standing at one city, we look along a road. Is the path through me shorter than your guess? If so, we lower it. You might think breadth first search would work. It spreads outward ring by ring. But it counts roads, not distance. Here it takes the 3-road path, costing 10. And it misses the 5-road path that costs only 9. Fewest roads is not the same as shortest distance. We must spread by distance instead, and here is the heart of it. We always take the nearest unfinished city. The moment we choose it, its distance is locked, beyond any improvement. Every other unfinished city lies at least as far, and since no road is negative, no detour through them could arrive more cheaply. So the closest city is final. So we keep 2 groups. Settled cities, their distances locked, shown in green, and the frontier, glimpsed from settled cities, each one holding a tentative guess, shown in blue. At every step we take the smallest guess. We settle it and relax the roads leading out. Now the whole journey. A begins at 0. Every other city begins at infinity. We settle a first. Relax its roads. B becomes 2. C becomes 4. The smallest guess is B at 2. We settle it. Through B, C improves to 3. And D appears at 9. The smallest is now C at 3. We settle it. And E appears at 6. C's old entry, the 4, still waits in the heap. When it surfaces, C is already settled, so we skip it. Now, a question for you. E sits at 6, D at 9. Which settles next? E at 6. Through E, D improves to 8, and F appears at 11. We settle D, and F improves to 9. At last, F settles at 9. Trace the path, A to B to C to E to D to F. 5 roads, summing to 9. The settled order, 0, 2, 3, 6, 8, 9. The wave reaching outward. Here is the algorithm, written down. The one new tool is a min-heap, a priority queue that always returns the smallest guess. Dist holds the best distance to each city. The heap holds distance and city pairs. We pop the smallest, the nearest unfinished city. If its distance is worse than one already settled, it is a stale leftover, so we skip it. Otherwise, for each road we add the lengths. Where that improves a neighbor's guess, we relax it. We lower the distance and push the improved pair. 4 details decide whether this works. First, negative roads break the promise. The answer comes back quietly wrong. So weights must stay non-negative. Second, a city locks only when we pop it, not when it is first seen. Third, A stale heap entry must be skipped, or we reprocess settled cities. Fourth, every distance starts at infinity. Only the start city begins at 0. So how fast is it? Watch the work. Every road gets relaxed exactly once. So each road adds a single entry to the heap, and the heap is kept as a balanced tree. Every push or pop takes a handful of steps. That handful is the tree's height, a logarithm. Multiply the two together. The whole search costs the number of roads times that small logarithm. Now compare it to brute force. Trying every route explodes exponentially. 1,000 cities, and brute force runs for an age. While this finishes in a blink, and it barely touches memory, we keep one distance for each city, and a heap holding at most one entry per road. That is all. The working memory grows in step with the map. No copies, no blow-up. Just the running guesses and a queue of what to try next. 6 cities, or 6 million. The bookkeeping stays exactly this lean. Let me show you the gap. Brute force fans into every possible route. The count of paths climbs past 100, then past 1,000 with no end in sight. Dijkstra spreads as a single wave. It touches each city exactly once. And it is already done. The same answer, 9. One does endless work, the other almost none. And this reaches well beyond maps. Though maps are everywhere. Every route your phone draws owes something to Dijkstra. The pattern is least total cost across a network. It guides packets across the internet through the cheapest hops. It finds the cheapest chain of connecting flights. It steers a character around the walls of a game. Even a puzzle becomes a graph. Each state is a city. Each move is a road. See your problem in that shape. And Dijkstra is already waiting. So drop the stone and watch the wave. 3 things hold it all together. Weights that never fall below 0, which keep the nearest city always final. The rule of settling the closest city first. And from these, distances emerge in order, like ripples from a stone. A whole network of shortest paths traced by spreading outward just once. Want to keep learning? Come find us at academy.rudewright.com.